Hi everyone, I'm NIANYU, a PhD student from Peking University. Today, I'm pretty glad to introduce our group's recent research, Hey, Preparing Humans to Do Tasks in Self-Adaptive Systems, which was collaborated with my colleagues from University of York and Carnegie Mellon University. Okay, let's start with the evolution of software systems. Software system was initially designed to satisfy system requirements or objectives. However, those systems would require frequent human intervention because they were not designed to deal with uncertainty. This is the first stage of system development, and we call it pre-adaptive era. Around 2 decades ago, we came to the self-adaptive era, and the ultimate goal of self-adaptive system is to eliminate the need for human intervention while adapting to the changing circumstances. However, human operator can provide some expertise, which is not easily automated. Systems can actually benefit a lot from some human involvement. As a result, we came to the third era, the co-adaptive era, in recent years. And in this new era, human and system collaborate to achieve their objectives together with their diversity of skills, abilities, and availabilities. In terms of human involvement, there are 3 main design principles from the bottom up. The first one is to complement functionality, meaning that humans are integrated in an intimate collaboration with the system to execute certain tasks. The second one is to achieve understandability. In other words, humans must understand how the system operates and what is happening at the current moment or even the moment before. Otherwise, humans may mistrust the system, leading to an inefficient collaboration. The third one is to manage human preparation. Human can be distracted or focused on another task at the moment when the system requires his participation. The system must perform effective actions in order to get the human properly involved to maintain a suitable level of attention so that human can understand the task context before execution, thus improving effectiveness. To implement these 3 principles, we could consider human assistance of a certain task, system explanation, preparatory notification to an operator, each one as an explicit tactic which can be used to optimize system goals. Despite the fact that those actions or tactics can yield positive effects, it may also bring with costs. For example, preparatory notification can yield positive effects due to attention management and context awareness of the forthcoming task. It may also bother humans' current activities. So it is non-trivial but important to reason about when and in what form to use preparatory notification. Too late or too little urgency of the notification, and the human may not be effectively prepared. Too early or too much urgency, and the human operator's level of attention may progressively degrade prior to the arrival of the new task, thus wasting his preparation time. In this work, we will apply a formal framework by following our previous research for designing human-involved self-adaptive systems, where preparatory notification can be used as a tactic to proactively aid human operator and improve overall system utility. We'll model human and system as a stochastic multiplayer game and allow a probabilistic model checker to determine the optimal use of preparatory notification in an adaptation strategy. Key to this framework is the explicit use of human attention to refine human attributes model. To further understand how we implement the first 2 principles, please refer to our previous work. Before we dive into the modeling details, let's take a look at a high-level view of the time axis for human-involved strategies with preparatory notification. Our preparatory framework will proactively notify the operator before assigning the task by taking into account an arbitrary look-ahead horizon. The lead time here denotes the interval between the instant in which the notification is received by the operator and the start of task execution. The optimal lead time will be the minimum time required for an operator to make a full preparation. Preparatory notification can be used as a tactic to simultaneously manage human attentional shift and context awareness. Attention management is about how much mental concentration an operator has on a task, whereas context awareness is about how much understanding the operator has of that task for efficient task performing. In terms of the attentional shift, its speed is greatly influenced by the type and urgency of the forthcoming task, as illustrated in empirical studies from the field of psychology. And we combine these two factors by introducing task priority, where high priority denotes a type of important task with high urgency. This figure illustrates two curves that exemplify how human attention diverges from the task at hand to the forthcoming task for different priorities. The left plot depicts a quick startup for a high priority task as operators promote their attention to its maximum capacity in a very short time. The right plot describes a slow startup where a human operator takes some time to gradually focus on. This is probably because the operator is very focused on the task at hand, while the forthcoming one has comparatively low priority. In terms of the context awareness, there are two factors: training level and context complexity. Context complexity denotes the amount of information required to perform a task in an efficient manner. Training level contributes to the ability of assimilating context information faster. Thus, time to achieve context awareness is intuitively proportional to the complexity, but inversely proportional to the training level. Besides, attention could also affect context awareness. It is intuitive that when an operator is not paying much attention to a task, he cannot efficiently comprehend the context even with a high training level. Thus, we introduce the concept of the ratio by referring to the ratio of the training level that can be exerted under a certain attention level. As we can see, under the attention threshold, the operator is not able to logically process the context information, no matter how well trained she is. With more attention, she can gradually increase her potential to understand the context. Of course, the curve could be very different for each person, especially for an expert and for a novice. To this end, we'll take three factors into account: task priority, context complexity, and training level to synthesize adaptation strategy. The optimal lead time of preparatory notification will be figured out by modeling tracking the stochastic multiplayer game, so that the operator will be informed with the right time and the right form of the notification to make proper preparations. Our running example is a very popular delivery scenario where an operator and a mobile robot collaborate to complete the delivery task as soon as possible. Semi-autonomous mobile robots such as Amazon's goods are supported by a human operator who can assist by generating delivery plans. Once a plan is provided, the robot will follow the plan without any human intervention, automatically avoiding obstacles to reach its delivery points. During delivery, human operators are free to do other tasks, while the system monitors the robot's progress and tries to notify the operator back to the delivery task when the robot is near completion. Without preparatory notification, the time required for an operator to generate a plan may be much more because she may need to shift her attention to the new task and understand the new conditions and context. But following our previous work, our approach to reasoning about preparatory notification builds on a recent technique, which is known as stochastic multiplayer games. In stochastic multiplayer games, players can follow strategies to either cooperate to achieve the same goal or compete to achieve their own goals. Model tracking then enables reasoning about strategies, optimizing an objective in reward-based properties. Our delivery running example is then modeled as a stochastic multiplayer game. Here is the player definition. Player environment is in control of all the actions that the environment can take, while player operator specifies the actions controlled by the human operator. Player system controls all the actions that belong to the robot and the controller. As for the environment player, for simplicity, we assume our environment model only keeps track of time. As for the robot player, this figure shows the encoding of robot behaviors in the collaborative delivery task. Variable lead time represents how much in advance, before the end of the current delivery, the controller should inform the human operator. The module includes 4 different commands that model the progress of the delivery. Delivery trigger, delivery update, delivery almost done, and delivery complete. In delivery almost done step, the robot will send a message to the controller so that the controller will inform the operator to proactively make preparations. In delivery complete step, the synchronization here will be triggered to inform the operator to start making plans. For the operator player, it is split into two stages. In the preparatory stage, we have three steps. Step 1. Preparation trigger. With preparatory notification from the controller, operator will start preparation with some probability, as the operator may ignore the notice message. Step 2. Preparation update. If successfully notified, the operator will gradually shift his attention and comprehend the context by taking into account three factors, namely task priority, context complexity, and training level. Besides, there is another step, time waste. The command here denotes the situation in which the operator has already achieved preparation before the robot completes its delivery. Thus, there is an economic cost that corresponds to the operator's idle time that could have been spent performing other tasks. On the task execution stage, there are four steps: planning trigger, planning update, planning complete, and follow up with preparation. In this command too, it depicts the situation when the operator started planning task with unfinished preparation, especially when the preparation time is insufficient, or when the operator missed the notification message. The operator will spend additional time shifting his attention on comprehending the planning context, leading to a higher planning latency than expected. With the modeling of all the players, we want to answer how can the outcome of adaptation with preparatory notification can be predicted for human-involved self-adaptive systems? How can a self-adaptive system determine when and in what form preparatory notification as a tactic should be provided to a human operator in a given situation? To do the model checking, we'll quantify the system objectives with utility profile. The listing here illustrates how a reward is defined for any successful delivery, and how a cost structure can be defined with a cost value if a human operator is idle. For each space of our problem, our model checker will obtain the system utility by subtracting the wasting cost from the delivery reward. To set up our experiment, we consider two types of operator, expert and novice, with different training levels. We also consider two types of task with high priority and low priority, corresponding to different attentional shift. The analysis result here illustrates the maximum accrued utility the robot, together with a novice, can achieve for various context complexity and various lead time on a high priority task. We can observe how utility increases first and then reduces with the increasing lead time. Longer lead time does not always bring better results and may weaken system utility. This is due to the cost of waiting. Also, the optimal lead time generally increases with the increasing context complexity. The plot here depicts the utility for a task whose priority is comparatively low. In particular, we observe that this plot is much flatter. The peak here occurs with a higher lead time compared to plot A with the same context complexity. This is because attentional shift for a task with low priority is much slower, and managing human attention to a required level takes a longer time, demanding an earlier preparation. This plot presents the result of tactic selection among emergency notification, normal notification, and temporary waiting, given the strict time horizon constraint on human involvement. As we can see, emergency notifications are mainly distributed in the upper left with very limited time horizon. This is because the time is too limited for a novice to be fully prepared with a normal notification. An emergency notification allows the operator to be more alert and shift his attention faster so that he can understand the context as much as possible within a time frame. Here are the results for an expert. Interested reader can refer to our paper. Okay, to recap a little bit, we presented a general framework based on probabilistic model checking to determine when and in what form a notification should be used as a tactic for attention management and context awareness. Actually, this paper is just one step of our series of human-evolved adaptive systems. Although one limitation of our evaluation is that we did not directly correlate our results with actual systems through an empirical study, and although we lack a direct procedure for obtaining the task priority nor the process of attentional shift, our results are supported by and consistent with existing empirical user studies from psychology field. Also, we only consider one operator for a delivery planning task. Scenarios with multiple tasks and operators can also be considered in future work with additional task delegation or task allocation. Yeah, that's the end of this presentation. Thank you.